Hello everybody. So far in this chapter on cement and concrete, we have looked at the qualities and properties of the ingredients, and then we took a look at some of the processes that are involved in actually putting together the concrete in practice. Today, we're going to talk about concrete properties. Now, of course, we talked earlier about the fact that cement hydrates by reacting with water, and slowly this leads to the setting and hardening of the cement itself. Now, please remember that concrete is a conglomerate which is made with cement, water and aggregate. So, what happens is the way that the concrete sets is not exactly the same as the way that the cement sets. Please remember, in cement we talked about the use of this test called YCAT test to determine the setting time of the cement. Now, of course, concrete also sets because the cement is hydrating and gaining strength, but the setting time of the concrete may not be exactly the same as the setting time of the cement. Okay, so you need to actually measure setting time of the concrete. Typically, that is measured by a process called penetration resistance. Now, this generally involves that you take the concrete which is fresh, you sieve it through a 4.75 mm sieve so that you remove the coarse aggregate, and you collect the mortar. And this mortar is collected in a cylindrical container, typically about 6 inches or 150 millimeters in diameter. And then you have these needles which are attached to an apparatus which can actually measure the resistance or pressure that the needles give when they are being penetrated into the concrete. So, as the concrete gets harder and harder, the needles will give more and more penetration resistance, and that is recorded as the setting time of the concrete. So, there is initial setting and final setting, just like in the case of cement. Okay. Now, from the practicality issue, the initial setting time is obviously important because it tells you the amount of time that you have to complete all the processes related to concreting, right? That involves placement, consolidation, finishing and so on and so forth. So, all those things need to be completed while the concrete is still pliable. Once it goes past its initial set, the concrete cannot be moved around freely, okay, without causing some distress in the concrete. And final set is important from the point of view of having attained a final form for the concrete, and that basically means that you cannot really alter the shape anymore beyond that point without failing the concrete. Okay, so and that's also important because we can know when to start removing the redundant formwork, which is not really supporting the concrete from underneath, but which is on the sides, which is basically defining the shape of the concrete mold itself. Okay, again, just to emphasize once more, concrete setting time may be quite different from cement setting time. This is again an issue because concrete setting is also determined by the cement paste to aggregate ratio. It's also determined by the presence of these mineral and chemical admixtures that we add to the concrete. When we look at cement setting time, we don't add any of those ingredients. Okay, we test cement setting time as it is, whereas for concrete we test it as the concrete mixture has been prepared with all the additives. So, because of that, you need to ensure that you have some sort of an idea about how long it takes for concrete to set. Normally, when you don't have admixtures, the initial setting time of concrete, it will be typically between 2 to 3 hours. Normally, okay, when you don't have any admixtures. With the presence of admixtures like water reducers, for instance, your setting time may go up to 4 to 5 hours. Your setting time may extend up to 4 to 5 hours. Okay, but you need to ensure that it doesn't extend too much, or in other words, you don't get what is called a set retardation. And in some sites, it is very common that sometimes when you overdose these chemicals or chemical additives that are added to improve the early age properties of the concrete, you may experience set retardation, which can completely cause the concrete to not set for several days on end. And this is a common scenario at many job sites where they add additional admixture to ensure that they are getting the required properties. Okay, but anyway, that discussion is a subject of a different course, probably a higher level course in concrete technology. Okay, so once concrete sets and hardens, it starts gaining strength, right? Concrete starts gaining strength rapidly at first, and then the rate of strength gain slows down. Usually, as in concrete design, we are familiar with the use of concrete strength at 28 days. We generally talk about 28 days strength. Okay. So, In most cases, you will see that concrete is specified in terms of a grade. We specify, so grades of concrete is, let's say, M30, M40, etc. This means that a concrete cube of 150 mm side, okay, 150 millimeters side cube, which is cured under water at 28 days, gives a strength of 30 Newton per millimeter square. That is what is meant by M30. 150 mm cubes cured under water at 28 days gives a strength of about 30 megapascals or 30 Newton per square millimeter. Of course, there is a lot more statistics involved in this definition. I am not going to go through that right now. Essentially, the number indicating the grade just tells you the 28-day strength. Now, concrete hardens, as I said, rapidly at first. So, in most modern concretes, you will see that by 7 days, you will get 50% of, by 7 days, you will get 70% of 28-day strength. By 7 days, you already would have attained 70% of 28-day strength. And generally, that is the point when we usually stop curing. Okay, curing is usually stopped by 7 days because your concrete has attained about 70% of its strength. 28-day strength is not the ultimate strength of the concrete. Concrete, if it's continuing to have a moist environment around it, that means that water from concrete does not dry out to the surroundings, then the cement in the concrete will continue to hydrate and contribute to strength. Okay, so concrete may continue to gain strength even beyond 28 days, sometimes beyond a year even, but the incremental strength gain is going to be limited beyond 28 days. Unless you are using special cements like fly ash based Portland pozzolan cements, in those cases there will be significant gain beyond 28 days also. Okay, now what affects the strength? The main factor is the water to cement ratio. The ratio of the mass of water to the mass of cement in the mix is the primary factor that governs the strength. The other factors may be cement content. Okay, to some extent, if you put more and more cement, you get some increment in the strength. Even keeping the water cement ratio constant, if you increase the cement content, you are going to get some increment in the strength to an extent, but beyond that you will start seeing that it drops. The type and amount of aggregate, depending upon the type of aggregate that you use, limestone, granite, andesite, quartzite and so on and so forth, and how much of this aggregate do you have in your system, that is aggregate to cement ratio, can also determine the strength. The type of curing and the extent of curing. Are you doing water curing? Are you doing curing compound based curing? Are you covering with a wet Hessian cloth, right? And how long are you going to be curing for? 1 day, 3 days, 7 days, 14 days? And that will also determine the ultimate strength that your concrete actually attains. The age of the concrete, obviously, as I said, at 28 days, you are getting potentially the main strength of the concrete. Even that is not 100%, it's about 90% of the overall strength that concrete can actually attain. But we consider that enough for design purposes, because that's a good check for us to see whether the concrete quality is correct or not. Okay. As I said, 7 days you already achieve about 70%. By 3 days, typically you will be achieving around 30 to 40% of 28-day strength. That may change depending upon the type of cement and so on. Some cements are rapidly hydrating, they gain strength early, like we talked about rapid hardening cement. In those cases, you will get much higher levels of strength at the early ages and then a slowdown in the strength development at the later ages. The ambient conditions can also dictate the strength. For example, if you have a very drying environment, it will remove the water from the concrete and that will lead to a low rate of hydration and that may lower the extent of strength. Okay, so you need to keep your environment moist. If the temperature is high, it will speed up the reactions in the initial stages. Okay, but then if the temperature is high throughout, it may again cause some issues with the hydration and lead to a lowering of the strength. So, all those factors need to be governed carefully. Interestingly, strength is also dependent on the specimen geometry. In some countries, we test cubes. As I said, 150 mm cubes are tested in India for the strength of the concrete. But if you go to some European countries or even the US, they use cylindrical specimens. Cylindrical specimens have a length to diameter ratio of 2. Okay, the height or length of the cylinder is twice the diameter, and that usually results in a strength value that is lower than what you get from cubes. We will talk about that in just a minute. Main thing, as I said, the main factor that affects the strength is the water to cement ratio, and this is a very famous relationship produced by one of the scientists named Abram, or Abram's law, that is what it is called. So, Abram's law states that the strength is a function of the water to cement ratio in some sort of a power function. Okay. Nevertheless, this need not be the correct form of the equation. Your strength basically is inversely proportional to the water cement ratio, that is all. It can have a linear relationship, it can have this power type relationship and so on and so forth, but that is not important. The important part to understand is, as the water cement ratio increases, the strength reduces. Now, of course, there is a limit to how much you can increase the strength by reducing water cement ratio. If you reduce water cement ratio, to some extent, your strength will keep on going up. But then, it all depends on how well you are able to compact your concrete. Concrete that has less water will be very difficult to compact. So, there will be a limit of hand compaction and the limit of vibration based compaction, beyond which you cannot really reduce your water cement ratio further. Okay. So, it is impractical to think of concretes which have very low water cement ratios. Now, what is that very low? Unfortunately, the definition of that very low has changed over the years. Today, it is possible to produce concrete with very minimal compaction, okay, which is almost flowing. In such cases also, concrete can be produced by water to cement ratios of as low as 0.15. That is the power of the chemical additives. If you do not have chemical additives, you cannot produce concrete of less than 0.4 water to cement ratio, okay, because it will be almost impossible to compact. Anyway, so all that depends on how much compaction you give. Why is high water a problem? As we have discussed before, in the initial system you have water and cement. Volume is occupied by water and cement, okay. As the cement hydrates, the hydration products fill up the volume. But if you have more water to begin with, you have more porosity. The more the porosity, the lower the strength, okay. So, generally we always talk about strength versus free water to cement ratio. What is free water to cement ratio? It is the water that is remaining after accounting for the water that has been absorbed by the aggregate, coarse and fine aggregate. Okay, we talked about water absorption of aggregate being an important characteristic to determine and what role it plays in actually controlling the mixed characteristics on dry days or rainy days. We talked about that previously, right. So, here free water cement ratio is whatever is remaining after accounting for that absorption. Okay, so please remember, strength is inversely proportional to water cement ratio. You do not have to bother about any law like this. You can't really, you can fit anything you want. See, today statistical data fitting is making things capable of fitting any sort of relationship through any set of data, but that does not mean anything. Okay, you need to understand the physical significance. Okay. Now, I was saying earlier that strength may be dependent on specimen geometry. In some cases, when you test cubes versus cylinders, you may get actually very different results. Okay. Now, why is this the case? In your mechanics of materials, you would have learned or will be learning a concept called Saint-Venant's principle. So, what that principle states that the end conditions which are there during the test will affect the specimen up to a distance equal to the least lateral dimension. So, what am I saying? What are the end conditions in the strength test? You have your cube or cylinder sitting between the loading platens, and the loading platens are going to compress the cube or cylinder. Okay. Now, the platens are made typically out of metal, and the concrete and the metal interface may have some friction. Okay. Now, because of this, when you compress something, the natural tendency for the material is to bulge outwards. There is Poisson effect. So, bulging of the specimen will happen outwards. So, what will the friction on the top do? It will try to prevent this bulging. Okay. So, in fact, the friction that is there between the platen and the specimen causes an increase in the compressive strength of the concrete. In other words, instead of plain compression, you get now a biaxial sort of stress state, which leads to an increase in the strength of the concrete. Okay. So, that is what is seen here. In a cube, the loading platen is giving compressive load, but because of the end friction which is trying to keep the cube from bulging out, you are causing some sort of a biaxial state of stress, and as a result you get a failure that is defined by this hourglass type shape. Okay, you get a failure plane like that. So, if there was no friction, if the end effects were negligible, if there was no friction, your true failure pattern should have been like this. You should have had vertical cracks through your specimen. Okay, if there is no friction, you will get vertical cracking because the compression basically causes an exceeding of the lateral tensile capacity. Please remember, for any material to fail in compression is very difficult. What typically happens is most materials that are compressed bulge out and exceed their lateral deformation capacity in tension, and that is why you get cracks which are parallel to the load here. You get cracks that are parallel to the load. Whereas, of course, when you have friction, you start getting cracks that get inclined, and that is because of the effect of the friction. Now, why is this any different in a cylinder? As I said, cylinder has L by D of 2. So, the effects of the end are felt only up to a distance of D from the ends. That means we still have a very small infinitesimal zone right in the center of the cylinder where the end effects of friction are not playing any role at all. That means we have pure compression at the central part of the cylinder. So, if you take a cylinder and break it, you will see that you get a failure which is more or less like this. Okay, you get almost vertical cracks in the center, and then there are some inclined cracks like that, and that basically is the failure pattern of a cylinder. Okay. So, cylinder strength, when you measure the strength on a cylinder, it is typically about 20 to 25% lesser, lesser than a cube. But one interesting thing that you need to consider, when a cube is cast, you put the concrete from the top, and all but one face of the cube are perfectly smooth because they are against the mold. So, typically when a cube is cast, what you do is you turn it by 90 degrees and then do the strength test so that you do not have to prepare the ends. In a cylinder, you can't do that. So, you take the cylinder, you pour the concrete and you cast the cylinder, and the same direction only you are doing the test. So, a cylinder is a more appropriate representation of a member like a concrete column, which is a vertical member where concrete is poured in that direction and the loading is also in the same direction. In the case of a cube, it is not the same. Okay. So, because of that, when you do your reinforced concrete design concepts, you learn that the cylinder strength is what is taken for assessing the compressive capacity of a column. Okay. So, please remember that the cylinder strength is the true compressive strength of the concrete. The cube strength is usually 20 to 25% more than cylinder strength. Okay. The same concept can be understood by looking at what happens when you change the height to diameter ratio of a cylinder. As I said, standard height to diameter ratio is 2, and that is where you get the true strength. What happens when you increase the height to diameter ratio? Usually you start reducing the strength. Okay. Not very significant, but yeah, you can reduce to about 10%. What happens when you reduce the height to diameter ratio? You get to a stage where you are almost, so at height to diameter ratio of 1, you are at the level of the cube. Okay. Even beyond that, you are causing significant increase in your relative strength. Okay. As you keep on reducing the height to diameter ratio, your relative strength is going up, and that is because of this aspect of Saint-Venant's principle. The end friction effects are going to be felt throughout the specimen when your L by D ratio starts getting reduced beyond 2. Okay. So, please remember, this is the reason why strength is not considered to be a material property, because it depends on so many test related factors. What about tensile strength? We always talk about compressive strength because that is what concrete is good at, but still for some applications we need to have some measure of the tensile strength of the concrete. Now, how do we measure tensile strength? You have to prepare a concrete and then pull it apart and measure the load at which the failure occurs. The problem with this, which we call as direct tension, is that it is very difficult to hold the concrete. I will come to that in just a minute. Before that, usually in most engineering applications, even if tensile strength has been proposed as a criteria in the specification, in most cases people do not seem to bother by testing the tensile strength. They assume some sort of a relationship, and that relationship generally pegs the tensile strength anywhere between 1/10 to 1/7 of the compressive strength. Okay. Tensile strength typically is about 1/10 to 1/7 of the compressive strength. But there are different methods in which you can measure tension. Tensile strength is, as I said earlier, in some applications like pavements and other applications where cracking can happen, tensile strength is important for judging the cracking potential of concrete. Okay. Concrete will crack only because its tensile capacity is getting exceeded, not because it is getting compressed. Okay. Please remember that cardinal relationship or cardinal truth about any material like concrete, brick or stone is that it does not fail because of compression, it fails more because of tension capacity being exceeded. Okay. So, what is direct tension? As I said, direct tension means you are simply holding the concrete and pulling it apart. But if the concrete specimen is large, the amount of pressure that you need to put to hold it together at the ends may sometimes cause crushing of the concrete at the ends. Your concrete at the ends may just crush because you are putting too much pressure to hold the specimen. Okay. Now, because of that, people try to adopt other means. One is, instead of holding it, you glue it to the platens at the end using a high bond strength epoxy. But sometimes that is a problem because it becomes more of a test of the epoxy strength rather than the concrete strength. Okay. The other thing is you can put a notch in the center of the concrete cylinder. A notch basically is a defect that you are already putting in. So, when you are actually pulling it apart, the failure will exactly occur at the notch. So, you are predefining the location of failure. Okay. But again, the acceptable test method obviously is the direct tensile test, because that gives you a clear response. Unfortunately, it is very difficult to perform, because of which we go for indirect methods. What are the indirect methods? One is called split tension test. Why is it an indirect test? Because we are not applying a tensile load here, we are applying a compressive load. So, we take a cylinder of the concrete and we subject it to a line load, a diametrically opposite line load, and that is what you are seeing. The section of that is what is shown here. You are compressing your concrete diametrically through diametrically opposite points. So, this is a compressive load that you are applying on the top and bottom across the diameter of the cylinder. If you take the element in the center of this concrete along the diameter, you will see that as you get away from the edges, as you get closer to the central part of the concrete, the lateral tensile effects are much greater than the compressive effects. Okay. Because when you are crushing in this direction, it will start splitting in that direction, or tensile load will be in that direction. So, if you take the stress distribution across the diameter, you will see that the top where the load is being applied is in compression, but a large portion of the cylinder is actually under tension along the diameter. So, what happens is, in that lateral direction, the tensile capacity gets exceeded and the concrete basically splits. So, in other words, concrete basically splits into two halves. That's why it's called a split cylinder test method, and it's called indirect because we are applying compression and not tension. Okay. So, here we can calculate the tensile strength quite simply with this equation: 2 times the load applied divided by pi times length times diameter of the cylinder. Okay. So, that is what is called an indirect tensile strength. The other way of testing the strength indirectly is flexure or bending. Okay. In most cases, tension becomes a problem when concrete is bending. Like in a beam, for instance, when you bend the beam, the bottom fiber of the concrete is under tension, and that is where it causes cracking. That is what exactly we do in this case of flexural strength determination. We have this beam which is simply supported, and we either apply a central load, that means midpoint load, or we apply what is called a third point load. Why is it called third point load? Because the distance of the load from the corners is exactly 1/3 of the span. This distance is exactly 1/3 of the span. So, the distance in between the loads is also 1/3 of the span. Okay. Now, the interesting part here is when you do this third point load test, you get a large zone here between the loads where shear is 0. You don't get any shear between the two third point loads. You don't get any shear, you get pure bending, okay, pure bending. And that is the reason why usually we prefer this third point loading arrangement. Okay, you would have all done shear force and bending moment diagrams in your mechanics of materials course. You will know that for this arrangement, you have shear and the shear changes sign exactly right under the load. Okay, in the zone right under the load, the shear will change sign. But in the case of equal loads, equidistant from the supports, you will have a zone in the center where there is no shear, there is only pure bending. Okay, so here what we do is, as soon as the first crack appears, we measure the load and the stress is then calculated from the load as the moment multiplied by C divided by I, where C is distance from neutral axis. Neutral axis in this case is right in the center. Okay, so C is nothing but d by 2 and I is the moment of inertia. Okay, right. So this is a simple arrangement for determination of tensile strength, indirectly again, because we are measuring the strength in bending.